Welcome to Insider's Guide, the show where we explore how young people can break into exciting careers, whether that's in tech, sports, entrepreneurship, medicine, etc. Today, we're diving deep into the world of semiconductors, designs, and application engineering. I'm Mahan.
I'm Ashrit. And I'm Aditya. Today we're joined by Hemanth Peddi, a principal application engineer at Cadence Design Systems, one of Silicon Valley's leading electronic design automation companies. Hemanth's journey took him from Chennai, India, to the University of Massachusetts Amherst, and now to the heart of Silicon Valley. He's worked on everything from cryptography, engines, and 3D stack memory ASICs to missile radar systems and IoT home automation.
And overall, everything combined, his path really shows how electrical engineering can lead to cutting edge work in chip design, verification, and tools that overall just power our world today, which is very much digital. So, Mr. Hemant, welcome to the show. It's great to have you here.
Thank you, guys. Thanks for the warm introduction. Hey, let's get started. Hey,
Yes. So how this is split up, we're going to split up into different sections. Our first section is our guest background and journey section. So let's just go ahead and get started. You're a teaching assistant at UMass while completing your master's. So how did teaching really help you understand complex engineering concepts better?
yes. So yeah, I was honored. I was really it was like a great opportunity to get a teaching assistantship back during masters. Uh, okay, how it helped me grow as a person. It helped me grow as a person and also in the technical aspects of it because so I was doing a teaching assistantship for a particular course called reverse engineering. The idea of, and it was first of its kind when I was doing masters. So the idea of reverse engineering course, as the name depicts, is basically uh, to address, uh, chip design is something, but understanding reverse engineering a chip from after it is built is a challenging aspect, right? So this course basically enabled users or enabled industry to reverse engineer or to understand how to do a reverse engineer on a chip. And that really gave me a very good aspect of actually how chip designing works because chip designing has many levels of integration in it, right? Starting from we call it RTL design, right? Starting from the RTL design until it gets a chip really gets to a tape out. Tape out is a technical word used when the chip is on a silicon platform, right? When the chip gets embedded into a silicon platform, that's called tape out. So this entire process, we are really understanding it in a reverse way, as in going from the last step again back to the first step. And the reason we do this in general, I just want to prolongate the topic there. The reason we do that is basically you have one company A, manufacturing or producing a processor, right? And you have company B, which claims that it's also producing a processor or an IP, but it claims that it's their own IP, right? To make sure that the company A has no part of company B's IP. Usually, generally, people do reverse engineering to make sure that two IPs are independent and they are their own intellectual properties and are uh, licensed to that particular companies, right? So yeah, so it helped me understand different aspect of semiconductor industry, my assistantship, and it really helped me motivate myself to be in this particular field because trust me or not, I had 60 members in my master's electronics batch, and only two out of the 60 people really went or stepped into the industry within the same field. Everyone else shifted to the computer science engineering because that was the hot topic 6 years ago or 7 years ago when I finished my masters, right? So yeah, that really helped me push myself, motivate myself to stay in the hardware industry.
All right, yep. Thank you for explaining that in depth.
That sounds great. So we're gonna backtrack a little and talk about your education at SRM Chennai. At SRM Chennai, you actually had a 9.172 out of 10 GPA, which is pretty impressive. And then you did your master's at UMass Amherst, as previously
Mhm,
mentioned. So, like,
mhm.
what specifically drew you to UMass Amherst?
Okay, there was kind of a motivation. So I would say there is no specific reason apart from UMass is a pretty recognized university in US, right? It was top 20 listed universities when I was searching for which university to get into, and it really inclined with my interests. Specifically, my interest was in chip design and verification, and generally, I went through the regular process like a student would do, like research in the professors, what the professors are doing in the university, what are the projects they are involved in, what are the courses that was available, and it really drew me. So one thing really drew me is that the professors at UMass, and I guess you guys being now that you need to decide which career to pick, right? Or which specialization to pick if you are in the tech industry or if you want to go towards engineering, right? So this is the same thought process you would be going right now. So what I did back in the day is, research about the professor. I actually applied for like 10 different universities, and I actually got a reject from North Carolina State University, and rest of the universities were accepting me. Yeah, it was like kind of the history of the professors. Most of the professors are from MIT. I couldn't get into MIT, and I didn't even dream of going into MIT. So yeah, so most of the professors were MIT professors, and I had a high expectation about the course. So that drew me in deciding to go to UMass.
So it's just mainly about the staff and all the professors, being very
Exactly, infrastructure. Yeah,
Yeah.
yeah, because
That is
because
important because, yeah,
yeah,
continue.
yeah. So because at the end of the day, university, no matter which university is a place to learn, right? The deciding factor between one and the other university would be the infrastructure and the quality of education that the university is giving you, right? Because it all depends on how much research is going on in a university, and what type of research is going on. So which needs to incline to your interest.
Okay, so now we'll be moving forward. So let's talk more about your internships. So obviously, a lot of your internships are very diverse. You did missile radar systems at Defense Research Labs, UART design at Electronics Corporations of India, IoT systems at HCL Technologies. So how did all these internships actually shape your career direction?
Yes. So, uh, yeah. So, it internships. See, getting education at a university level and applying it out there in the world are two different things, right? You get to know a technicality of something when you learn it, but you get to know how it really works out there in the world when you do an internship. So internship really at that time when I was 20 years old or something, right? So at that time it really helped me put me in a direction where I really understand the practicality of the technical knowledge that I have. Right. That really helped me to, focus on what what does the world is heading towards, right? And how does things really work out in the world? Because it's always a learning curve when you are a student, uh, it's very exciting to see learn things, but see it in real world, in real applications. When you really, like when you see, for example, you use Instagram application, right? When if you are, I mean, you might have done some part of coding right by now, right? You might be familiar with, I hope you are, right? So when you scroll through something on Instagram, and when you really develop an application like Instagram, you see the difference, because one thing is, by using Instagram you are getting educated on what Instagram is, but by developing an app like Instagram you are really seeing its practical applications, right? So that's the difference. That's really a eye-opening thing for me, having getting that opportunities in a pretty big companies in India. That was really good. Yeah,
And that's a good point you mentioned because there's a difference between being a consumer and being the person who actually makes the product for consumers to use. So yeah, that's a good
exactly.
point.
Yes, exactly. Yeah.
Discussion, which actually has four different subsections in it. So for our first section, it's understanding semiconductor basics. So, Mr. Peddi, you worked with encryption chips and 3D memory. What makes 3D stacking better than regular memory?
Restacking, yes. So let me put it in a layman terms, because the more technical words I use, it will be more cryptic for you guys, right? So assume the name, you understand the name 3D memory, right? It's nothing but having, instead of a two-dimensional sheet of memory, when you say memory, it's nothing but transistors, right? It's nothing but some part of logic, some part of transistor, which are holding, uh, to put it, holding ones and zeros, right? So holding the value of ones and zeros. And in design world, in digital world, ones and zeros are depicted as high voltage and low voltage when it comes to a real circuit board, right? So so 3D memory is nothing but when you stack a memory one upon the other, instead of in one slab of silicon. If you have two or three layers of memory, one upon the other, it's called 3D memory. And to explain it to you, suppose you three are friends, right? So imagine you are staying in an apartment, like an apartment community, where you are neighbors, or you live in an apartment which is one above the other. And the second scenario is you are friends, but you are living in an independent houses which are scattered, right? So suppose you guys want to meet, or you guys want to hang out, right? You go from one independent house to another house, which takes at least 2-3 minutes or 5 minutes, depending on the distance between the houses, right? But when you are living in the same apartment, stacked one upon the other, what is the benefit that you're observing? The benefit is that if you're going to go hang out or meet with one another, the traveling time is being cut short, right? You at max take 10 seconds, right? So the advantage of 3D memory is there is a concept called clocking, or there is a concept called transferring data in the world of semiconductors. So the, the time it takes to transfer the data between the chips, or the time it takes to utilize the data from a particular memory, is way faster when you use 3D memory, because it's all in one location.
Got it. Okay. So moving on to our next question. So when you first have your circuit design or prototype, how do you actually develop that into an actual chip? And what makes the timing so difficult to get it right?
Yes, so yeah, as I was talking about timing, right? So in my analogy that I did earlier, right? So let me explain you a different analogy. Okay, so timing is really important in the world of semiconductors. Imagine you have a football coach, okay, and the coach expects you to be on time at suppose 8 a.m., right? And the coach is so strict that he can't tolerate anything after that or before that. If he wants to be at 8 a.m., you have to be at 8 a.m. So in the world of semiconductors, like in the world of chip design or verification, there is something called sampling. Okay, so the data transferred between one entity to another entity is being sampled, and the, there are different types of timings, I would say. The one in the world of verification, or what we say when we say sampling, what we mean is there will be a clock, as in, when companies like Apple, Nvidias of the world, semiconductors of the world, introduce their chips, they call something like 3.5 gigahertz processor, right? What actually means by a 3.5 gigahertz processor? What does the 3.5 gigahertz mean, right? It means the speed at which the clocks, or the speed at which the chip works functionally, right? So this speed, consider there is a clock which is like a you want so when I say clock, it's like it's not the actual physical clock, or the time, the thing that shows you time on a daily basis. When I say clock in a semiconductor, it's a toggling signal which goes one and zero at a very high and very fast speed. So it's a signal, basically. The clock would look like a one and zero toggle, okay? And everything is sampled with respect to the clock. So timing is so critical uh, uh, because there are certain things. Suppose CPU is requesting for something, Okay, so you have an SoC, you have a platform, and CPU inside a device. CPU is requesting some data, right? And timing is critical because if CPU doesn't get the data correctly, it's just sitting there waiting for it, right? It's not able to proceed with with whatever it has to do. Like for example, we are talking on an application right now, right? So if timing is not set properly, even in in the world of networking, the packets that are being transmitted from one device to another device, if it is not timed correctly, there would be delay. There would be glitches between what I say and what you hear, and what my camera is capturing and what you are seeing on your screen, right? So translate that similarly inside a chip, inside a processor. The same thing happens. The data needs to be transferred at a high speed and needs to be sampled so that the processor get to do its thing, right? That's why, like, timing is very critical
Yeah, so the follow-up
within that
question on
case.
that.
Mhm.
So in terms of timing, timing is always going to remain a word, but how do you actually make a chip faster over time? Because, is that through constant testing, or like how do you actually make a chip keep going faster and faster, the amount of data it keeps sending over
Yes,
time?
so that's a good question. So uh, see, before a couple of decades, right, or before a decade, call it before a decade. Uh, you never hear Tim Cook or anyone saying that we have designed A1 processor, Apple call it A1 processor or whatever, right? With this particular speed. But why is timing so? Uh, is it why is it a mainstream right now? It's uh, because we are migrating from a technology where we had different parts of the chip sitting in different places to something called an SoC, right? An SoC is putting everything in one place, right? So the technology is getting advanced, and back then, when you see a PCB board, right, you know what a PCB board is. When you look at that green silicon wafer, even in your video games, inside a phone, inside a tablet, there will be a green and gold silicon wafer, right? It's a PCB board. So when you look at a PCB back in the day, all the uh, all the parts of the, like, a CPU or a memory, a GPU used to sit at a very vast different places, right? When I say vast, I use that word because the distance between these entities back in the day was very much very big compared to what we are seeing in SoC, which is like millimeter or even less than a millimeter, right? So right now we are at a 3 millimeter we are manufacturing out there 3 nanometer chips, right? When we say 3 nanometer chips, it's the size of the silicon wafer is so small, and the density of transistors that we are packing into the silicon wafer is so advanced, that it, the speed has that's the reason that the speed has increased so much, because the communication between the parts has been reduced to less than a millimeter. Earlier in the day, the communication needs to happen across the board, across the PCB board, right? And now we have developed something. In design, chip design, we rely mostly on protocols, right? There are different types of protocols. There are like peripheral protocols, and there are on-chip protocols, right? On-chip protocols are, when you look at a chip architecture, right, or a whatever processor architecture, you see there are different parts of it, right? There is a memory, there is a display port, there is a CPU, there are GPUs inside an SoC, right? So now imagine this these different entities talk to each other, but how do they talk to each other, right? They have particular protocols to support the communication between these different entities. So that's why we keep increasing the speed of a processor by putting things together within a chip.
Got
Yeah.
it.
Yeah, so moving forward, so now I'll just be talking more about your experience working with semiconductors. So you developed a chip level verification environments and adapted vendor IP test suites. With billions of transistors, how do we test that chips work? And also, what's the difference between functional and formal testing?
Okay, yeah, that's a good question. Yes. So I would like to tackle the first half of the question. So how do we test a billion gate chip, right? So there are different ways to test it. Actually, the question correlates with each other. The first half of the question correlates with the second half of the question. So when we develop a design, uh, uh, right? So to put it in simple words, right? For you to understand instead of getting into the technicality of it, the very simple code in the world is hello world, right? Writing in hello world, right? Either whichever language you pick, right? So this hello world, so let me explain the process of converting a hello world into ones and zeros. How does it happen, right? How does the computer understand when you type in a hello world, right? So this hello world, for you, it's a piece of code, but there are different layers of compilations that are going on for the computer, or for the computer to understand what you have written in a piece of code. So basically, your piece of code gets compiled into something called assembly language. Okay, if I want to break it down at a very high level, your piece of code that you're writing gets compiled into something called assembly language, and there is a tool that translates assembly language to machine instructions. Assembly language is a layer of it's another big field in our chip design and verification, where your hello world code gets converted into an assembly language, and assembly language is a human readable format. Then it gets converted to a machine readable format. Into the machine readable format is nothing but a circuit in terms of AND, OR, and NOR gates. I hope you know. Are you familiar with AND gate, an OR gate, and etc.? What are gates, etc.? Yes, right. So this piece of hello world code gets converted to an assembly language. Then gets converted to a machine language. Then it gets converted to ones and zeros, right? So when we are validating, or when we are verifying a billion gate design, what we do is there are different types of verification: formal and uh, functional verification, right? There is something called simulation verification, and there is something called emulation verification. So where I am in right now at Cadence, I'm an emulation engineer. I do emulation verification of a design. So simulation verification is nothing but, if you have the design ready, like the entire 1 billion gate design ready, just simulation, as the name says, that there are certain tools which simulates, or which makes sure to understand the design that you're writing in the 1 billion gate design, right? So this design that has been written, it is this, when we say 1 billion, we don't know yet that it will be a 1 billion design. That happens in the later stages, right? So there will be a piece of code lying out there that the design engineers write, which will be in Verilog, or System Verilog, or VHDL. Uh, this is a programming language. It's a Verilog or System Verilog. This is almost similar to high level languages like C, C++. Right? If you know C, C++, you would be able to write, and if you know basics of design and verification, you would be able to write a piece of code in System Verilog. So this System Verilog is then optimized, is then simulated as in, if you write a piece of code, there will be something called waveforms. Then you look at the waveforms, you simulate the design. You simulate as in, you know what signal is behaving which way, what piece of code is behaving in which way, and then you verify it using simulation, and then you are done. If there are any bugs in the design, if there are any corner cases that you hit, you verify it, and then you provide the feedback back to the designer to fix those bugs. Then you are done. But when it comes to emulation is an on-chip verification, as in, you now have a design lying out there. Now you compile it. There are different stages of emulation, but at a high level, you compile the design, which is 1 billion gates, and you map it to an to the emulation platform. So you do real time testing of the design that is in your Verilog code, right? That's the emulation part. So simulation is not real time testing. It's just predicting that the design would work this way. Emulation is actually testing it real time with giving real clocks. So that's the difference between functional verification and as simulation verification.
Thank you for explaining that.
Yeah,
Okay.
that was a great explanation. So moving on to our next subsection, which is EDA tools and customer work. As a principal application engineer at Cadence, how are you seeing AI and machine learning transform EDA workflows? And what's your experience with newer gen AI-driven design optimization tools?
Yeah, so I, see, AI is a new new tool in the market. It's not yet reached. I would say companies like Cadence. I would like to pitch in my company, who is developing something called agentic AI. So I would say that AI is really a tool which helps engineer write a better piece of code to do something in a better way, optimize it in a better way, so and reduce the time to deliver things. So that's I'm thinking that when AI gets into the system, people will work better than better in terms of providing uh, optimized piece of code or optimized piece of work than it is right now. So the time to bring up something, the time to bring up something from a thought to an actual product, the time which it takes will be reduced a lot when AI is introduced out in the market to the engineers.
So like everything, just like, the production timeline just goes like becomes
Yes,
short.
this becomes shorter. Yes, yeah, that's where the agentic AI comes into the play, right?
Yeah.
Right.
Yeah. So moving on, moving from lead to principal application engineer, what does customer facing mean in cutting edge technology? And how do you help customers with huge complex chip designs?
Yeah. So the application engineering is a customer facing role. When we say customer facing, it means that we are I am representing Cadence at a particular customer, and I'm helping our clients or our customers to bring up their designs using the emulation platform that we have. So I'm well trained and well knowledgeable on the Cadence platform, and there are different aspects of it, compiling and then verifying it on emulator, and different types of verifications are there. So yeah, I help I communicate with the customers about their need, about their specification, about what they really want to do, and be a bridge between Cadence and any other customer, and help them bring up their designs using the Cadence proprietary tools.
So you basically just imagine their designs and make it a reality, right?
Yep, yep,
Yeah.
yeah. So, yeah, kind of imagine. I consider them as a black box. Black box, as in, I don't know anything inside inside a box. So that in the world of uh, not only verification, but I would say outside in engineering, we call something black box if you don't know anything about it, right? So as a Cadence employee, I don't know anything about customer chips or designs, right? It's their proprietary design, right? So I consider that as a black box, and now they give us specifications. See, this black box needs this kind of a support. These are the specifications this black box works on. So we consider all the inputs that the customer needs, and then we support it, and we provide them the best support using our Cadence tools.
All right, so last question for this section. So we talked about how chips over time they become very, very small, but that doesn't mean they're still not complex. They're very much complex. So could you explain more about what place and route tools are and how they work with these tiny transistors?
Yeah, yeah. So place and route is a very niche topic, right? Uh, for you to explain place and routing. Okay, let me think. So place and route is nothing but it's a pretty popular term in the world of prototyping. So prototyping, we call it prototyping when we are using something called FPGAs. Have you ever heard of FPGAs? So have you ever heard of Arduino? Arduino, yeah.
Yeah. Arduino.
It's a processor in itself, and you can play with it. The Arduino is a kit, is a hardware kit. If you're really interested in electronics as a major, going into your graduation, you need to get your hands on kits like Arduino. There is another kit which is the Arduino is an ASIC, okay, but there are equivalent kits which are made up of FPGAs. So there are two different worlds. One is an FPGA world, one is an ASIC world. Okay, FPGAs, it stands for field programmable gate arrays. Okay, FPGAs are made up of something called LUTs. Okay, and you so there are many companies which provides FPGA solutions, Intel, Xilinx, etc. Okay, so consider this. Okay, ASIC is something that is predetermined. You have an ASIC. It is supposed to only do this one thing. Okay, suppose suppose you say you give a specification. Suppose you tell a robot to just clean the surface, right? And you for that particular process to happen, you have an ASIC which only does one thing, uh, which only supports the cleaning of the which only supports the robot which cleans the surface, right? And it only supports the piece of code which goes into that particular program. But FPGAs are not like that. FPGAs are field programmable, as in on air you can program that processor on whichever application you want it to be used for. You can program FPGAs as whatever what suppose you have an idea in your head that you want to put it put it out there and implement it. So FPGAs are the ones which you use to mimic any any processor or anything that you want to build, basically, because it can be programmed on air. So that's the difference. ASIC is predetermined. It only does one thing. FPGAs are not like that. FPGAs can be programmed to address multiple scenarios, multiple projects, etc. So in FPGAs, you do place and route. So the place and route comes in terms when you talk about FPGAs. So place and route is nothing but converting your design and placing inside the FPGA logic. That is called place, and route is nothing but routing, as in connecting different parts of your design using the actual silicon inside the FPGA. That is place and route.
So moving on to our next section, we're going to go ahead and talk about more about the future of chip design. So there's a law, it's Moore's law, which says it's more about slowing down, but we're using chiplets now. So how are design tools adapting to multi-chip designs?
Uh, yeah. So see, we should say how are multi-chip designs adapting to design tools, because design tools comes first and then we get to design multi-chip designs, because if there is no tool, there is no design, right? So all the EDA companies, think about it, right? If a company is producing a chip, a 3 nanometer chip, uh, uh, the R&D work and the process of writing the design, placing it inside a silicon would have been done 5 years ago, right? If a chip, if you are looking at an A15 Bionic chip that or A17 Bionic chip that Apple is releasing right now, the process of writing it, validating it would have been done long back, right? It would have been done at least 2 years ago, so that they can test it, they can verify it in real world applications, and then they release the product, right? So I would say EDA tools are way ahead of way ahead in future. Only then it is possible for rest of the companies who are using EDA platforms to design and put their products out there.
So it just depends on the tools.
Yeah, that's right. Yeah, tools need to be developed first. Only then the product comes in.
Moving on to our next question, you also built accelerators and worked on advanced ASICs. So how is designing AI chips different from like traditional processors, right?
How was accelerators different
How's designing AI chips different?
or design AI chips? Uh, mm, See, design AI chips. So all these companies, what they're doing right now is designing their own processors. Like Google designs their own Tensor chip, Apple designs their own Bionic A15 or A series chips or M series chips for their watches and all. So what is it? What is difference between these and a Qualcomm processor, right? Every Android out there has a Qualcomm processor, but some companies have their own chips, right? So the thing is, it depends on. So now we are going on a reverse pyramid approach. So the reverse pyramid approach is that now you have until now in the world of engineering, we always did a pyramid approach, as in you first have the base, that is your processor, right? And then you decide on what you want to build on top of a processor, right? It's a pyramid approach. Now reverse pyramid is that now you have in the world of AI, like Google knows or Apple knows that it needs to address image processing, or it needs to address like there is a gimmick, right? Now you ask ChatGPT in some simple words to generate an image, and it generates for you, right? So similarly, they would have predicted this generation of AI long back, right? So now they are building processors to support such intense programming, right? So now we are following, at least in my terms, I call it reverse pyramid approach. I don't know if out there if that word is practically being used out there, but I call it reverse pyramid approach because now we are creating processors depending on the use case scenarios. Earlier, it used to be that the processor used to be built first, and then the use case scenarios used to be developed next. Because now the thinking and now in the world of AI, we are it's basically being reversed.
Got it. And just a follow-up question. So now that we're on the topic of future trends, where do you see
Mhm.
the correlation between quantum and semiconductors? Do you see a correlation some other?
Uh, yeah, so the quantum computing is something different, right? Uh, I personally believe that quantum computing will be the future going ahead. But I don't have much knowledge on quantum computing yet. Even I am it's a learning curve for me as well. So I just have a high level idea of what quantum computing is, but I don't know. But I at least believe that quantum computing is the way to go in the future.
So now we'll be going into our next question. So your crypto engine work involved AES, Blake, and other standards. So how is security being integrated throughout the entire design flow now?
Yeah, so yeah, that's a good question. So now, see, security is a major part of a chip design, right? Because there should be no data leak. There should be even inside a chip. Trust me, there are 100 million ways to get the data out of a chip, right? So security plays a major role even in verification and design, even in chip hardware design and verification. Security plays a major role. The ones that you said, AES and SHA, all these are uh, cryptography related protocols out there. But yeah, in general, security does play a major role, and to secure a chip which is of billions of gates, it's there is a process, there is like uh, a predetermined set of rules that they follow to secure a particular chip, right? So it is very difficult to break it out, but uh, there are protocols that we follow, that the companies follow to secure a chip.
Okay, thank you for explaining that. So now I'll be going on to our next subsection, advice for high schoolers. So majority of the audience is high school students, which is why we like talk about this. So from your experience, what are some foundational skills that matter most for breaking into semiconductors itself?
Into semiconductors. Uh, okay, so one thing is you need read a lot. Okay, reading is a very good habit. Read a lot about so when whatever you hear, whatever you see out there in the world, now that you have pretty good AI based platforms like ChatGPT, Gemini, etc. So try to understand things in a different way, right? So whenever you hear about something, we hear about company doing something, X company, some company doing something. Uh, Try to better understand it a little bit at a high level on what it is. Suppose you are attending an event, you're on air, on live, attending Apple's event, right? Not only look at the product, but look at if you want to go into semiconductor, look at the details that they're giving. Why are they comparing the performance of a processor with last year's processor? What does the performance mean? Dig deeper. Just try to understand every word in the keynote to really, make more sense of it. Then you will, if you are interested and if you are doing that, that means you are, you are really interested in an electronics major, right? If you read about it and if it doesn't excites you a lot, stay away from it, right? So one other thing you can do is, I said Arduino, right? It's a processor. It's a kit that you can use to develop. It's a you can I think right now Arduino also supports Python based processing, right? Or Python based coding. It's a kit to develop robots. You can play with it, create a small robot with it, see how it goes, see if you are interested, see if it excites you, right? Before taking your career decision. Right? So I would say that you need to practically work on at least the bare minimum things that are available. Suppose you want to take you want to take gymnastics as your future, right? You want to be a gymnast. So in that case, what do? You as of now, you go, you practice every day, you see how you're performing, right? Basically, you go to your trainings, etc. Similarly, engineering is such a thing that you need to get a hold of something that you can practically work on, then decide, if this is something. And I would say, talk to people like industry professionals, understand what it goes to be, what it goes inside a chip, what it means to be a hardware engineer, and analyze it, right? So your decision of picking a major as a high schooler should be majorly dependent on two things. One is research, talking to the people, industry people, and understanding things in a different way. And second is your interest. So these two things should play a role for you in deciding your career or the next step in your career.
For sure. It's very important to like talk to people who are experienced, like you are. I was talking to you just to get an insight of what you're getting
Mhm.
yourself into, right?
Yes.
So yeah. So also from your experience, you're pretty well versed in C, C++, System Verilog, and VHDL, which you've mentioned previously. So which programming languages or tools should students start learning to get ahead? And like you also mentioned Arduinos. Like, are there any specific projects that people should use? I mean, using Arduinos? Or
Yeah, no, see, Arduino is a versatile product. You can build anything with it. It's a processor, right? You can build anything with it. So get onto it. There are free open source projects available out there. Where you can download them and try it out on Arduino. Like very basic of it, like for example, a digital board, right? Or you code something in an Arduino, and the digital board will display a counter. The digital board is nothing but it has LED lights. It counts from 10 to 0, like a counter. Simple projects like that. And you can also build like complex projects like a line following robot, or a okay, like a traffic sensor. In my undergrad, I actually got and developed something called a line following robot. I hope you have seen some reels where a robot follows a line at a very high speed, right? Those are the things that you build out of an Arduino. So pick up something on from online. It should be there out there.
so, and also like any specific programming languages, or is it just like C++ because that's
For
what,
the programming language, yes.
yeah.
No, I would say high-level languages are important. You need to know how to code in C, C++. That would be the base of it. Base of that would be the foundation for your coding career. But I would say you also need to get familiar with the hot ones out there, like the Python, Perl, etc. So, yeah, but C, C++ should be your foundation.
Moving on to our last question for the section, we're going to go ahead and talk about internships. Working at a real company, that's where you get the real practical experience. So, do you have any advice for high schoolers looking to actually get good internships in semiconductor industries? And something I also like to mention is that goes hand in hand with other industries as well, whether that's robotics, automation, things like that. So, what advice do you have in terms of getting an internship there?
Uh, so I would say, see, as an high schooler, I don't think companies would expect much from you. right, to do an internship. And your internship, uh, uh, so are you asking about internship after high school, or are you asking about internship during your undergrad? Like,
We could talk about both. So we could talk about before high school and then after high school as well.
yeah. So see, I don't know how much of a gain it would be by doing a tech internship, right? Right during your high school. But because think about it, like companies hire you as an intern, and the moment, I mean, go out there, see if there is any position available as an internship. But I would say it really doesn't matter which company or where you're interning it at this level. Because the main important thing that you need to do is secure a internship. But after securing an internship, no matter which company it is, right? Just target an internship. Don't target the company. Target an internship. But the main thing is you you need to grasp and understand everything that the process the company follows, what the product that the company follows, and then understand it. Or I would say, if you are really interested to do an internship, go after the product that you are really interested in, right? Is it a chip that is products are very vast. There are different vast products, right? And you know company based on its product. Like for Cadence, it's an EDA platform. The product of Cadence is an EDA platform and an emulation platform. The product of Apple as a company, there are multiple products that Apple produces, right? So see which product you are interested in, and then go find an internship there, right? There are multiple in this generation. There are multiple such companies, like multiple products. Everything is product based. Every company is a product based company, right? The product be is it a B2B or a B2C, doesn't matter, but every company is a product based company. So I would say look after the product and then decide which company you would like to intern at, right? But the process after getting an internship, just make sure to grasp everything and just think out of the box, right? Because because compared to me when I was in high school, you have very powerful tools in your hand, right? To understand things out there. You have a phone which has like AI softwares in it, which will explain you each and everything in detail. So just make sure to grasp everything when you are interning.
Sure. So we'll be moving on to our second to last section, which is rapid fire Q&A. Just say the first thing that comes to your mind whenever we ask these questions. So our first question is one book you'd recommend to high schoolers, college students, even people in the
Mhm.
industry that are interested in tech that really helped you with with
Okay.
semiconductors, focusing on anything.
Okay. I would name a technical book, but I need to think think of you as a high schoolers, and then you need to read it, right? So I would say there is a book called The Innovators. You should really get hands-on onto that book. I think it's by Walter Isaacson. It's a really good book which describes many people's efforts in innovating something new, right? It describes many. It's a collection of uh, 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 as the name suggests, innovators, right? It's a collection of life stories of people who invented something out there. So it will be a very, very motivational thing for you guys.
So if you weren't in semiconductors, what industry would you be in?
Ah, I would be a chef. I like to cook.
You'd be a chef. Oh, that's interesting. That's cool. Um, what's your favorite programming language?
My favorite programming language is Verilog, System Verilog, which is a hardware level programming language.
What is the most underrated piece of technology you see growing in the next decade or so?
Underrated. And I would say the use of AI in automation. No one talks about it, right? Everyone talks about all these gimmicks that the companies do, generating an image, generating a video, just via using a few sentences that you type in. But no one talks about how AI is being used in automation out there, right? If you go into a Amazon factory, everything is done with machines, right? Everything is sort of robots. It's a pretty big thing, and it's very underrated, I would say.
Yeah, it's great you mentioned that. Personally, I'm interested in autonomous technology, so yeah, it's great to hear
That's
that.
good. Yes,
Yeah.
yes, yes. Yeah.
And then what does your morning routine look like?
My morning routine. Okay, it's pretty basic, I believe. Go to the gym, come back, take some, spend some time with the family, start the work, etc. But I would say, morning routines are very important because it sets the mood for the day. If your morning routine is messed up, your day is messed up.
Okay, it just brings a positive mindset to start the
Yeah,
day. Yep.
yeah,
Yeah.
yeah. That's right. That's right.
What do you think of about the future of chip design in 3 words?
Future of chip design. I would say AI, agentic. I mean, specifically agentic AI. Um, more speed, uh, and 3D lithography.
So now we'll just be wrapping up, moving on to the closing thoughts. So, what's one final piece of advice for any student who wants to break into the semiconductor industry but feels overwhelmed by how complex it all seems?
Can you repeat the question? What
Yeah, so obviously
advice you're saying?
a lot of students
Mhm.
they want to break into the semiconductor industry. So but they most of the time they feel overwhelmed. So how do you think they should get into that industry and what advice would you give to them? Because obviously the semiconductor industry is very complex.
Yeah, I agree. Yes. So this notion of semiconductor field being complex needs to be go away. Needs to go away because see, whenever we see something very complex, this saying, we say it's not rocket science, it's easy, right? Who told you rocket science is hard? It's not hard. If you are interested, nothing is hard, right? Why are you comparing it with rocket science, right? No, semiconductor industry, in the field of semiconductor is not hard, it's interesting, right? So do not the notion of being complex, the complexity, it needs to go away. Semiconductor is a field which is growing, which is a hot topic right now. So don't even consider it as hard. If you are really interested in something, it will not be hard. So motivate yourself. Think of it as you are giving something out to the world because you are really putting in some efforts to make the world a better place, right? So not only semiconductor, right? Whatever you are doing, whatever you choose to do, just do it with all of your heart, so that it doesn't become complex to you. Only if you think it is complex, it will be complex. If you think it's easy, it's easy.
It's all about the mindset.
Yes, it's all
Mindset
about the mindset.
for sure.
But yeah, overall, thank you so much, Mr. Petty. And your journey really shows that, if you stick with your one passion, you stay curious, you stay available to learn more, you can remain persistent and really go into that industry and understand everything at a foundational level and even at a
That's right.
very complex level as well. So thank you so much for coming onto the podcast,
Thank you,
Mr.
guys.
Petty.
Thank you for having me. Thank you for
Yep.
having me. You can reach out to me anytime for any questions. Okay.
And
Okay.
that's our episode of the Insider's Guide. We'll see you next time.
Next time. See you. Bye.
Thank you.